So, we've all seen the movies, right? The big dramatic shot,
Oh, yeah.
a spaceship, maybe some poor astronaut gets a bit too close to a black hole and
Yeah.
just whoosh, gone.
Instantly vaporized or, sucked into nothingness.
Exactly, like a cosmic vacuum cleaner. That image is just, well, it's everywhere in pop culture.
And it makes for great visuals, definitely. But that picture, it's a huge oversimplification of what's actually going on. The physics involved are incredibly complex and, frankly, pretty violent.
Violent, not just a quick disappearance then.
Far from it. That idea of a clean, quick ending
Yeah,
doesn't really match the reality of the forces at play.
right, which makes you think, okay, what really happens then? If you could get close to one of these things, these cosmic mysteries, is it just poof? Or is it weirder? Maybe even like more terrifying?
Definitely weirder.
So that's kind of our mission for this deep dive. We've got some source material here, notes and bits from something called Surviving the Cosmic Abyss, the truth about black holes. We want to unpack the real science behind them.
Yeah, look at how they form, what they're actually made of, structurally speaking, and the extreme physics, governing everything near them.
We want to move past that sort of simple fear-based idea
Right.
and actually get into the science of what happens when you approach that edge, that event horizon.
The point of no return.
Yeah.
Exactly.
Okay, so the source stuff really emphasizes the mystery part first. I mean, they trap light so you can't see them directly. They feel like these invisible holes, which totally feeds that monster myth, doesn't it?
It absolutely does. And Hollywood loves that idea of just vanishing the second you touch the event horizon. Instant drama.
But what's interesting in the notes is how they shift the focus. It's less about the end, the disappearing, and more about the journey to that end, which sounds way more complex.
And violent, yeah. That idea of just winking out of existence, it just doesn't stand up when you look at the actual forces involved.
Okay, so let's back up. Where do these things even come from, according to the notes?
Well, they're basically the corpses of giant stars. Really massive ones.
How massive are we talking?
Stars that started out life with at least, say, 8 times the mass of our own sun, maybe more.
Okay, big ones.
Huge. And when these giants run out of their nuclear fuel, the outward pressure that was keeping them puffed up just fails. Gravity wins.
Ah, so everything collapses inward.
Violently. It collapses catastrophically.
And that's the supernova, the big explosion.
That's the supernova, yeah.
Yeah.
A spectacular death throw. But for these really massive stars, the story isn't over. If the core left behind after the explosion is still heavy enough,
Heavy enough meaning?
more than about 3 times the mass of our sun, if the remnant core is heavier than that limit, gravity keeps crushing it. Nothing can stop it.
Nothing. It just keeps collapsing.
All the way down.
Yeah.
According to Einstein's general relativity, it collapses. Well, theoretically, to a point.
A point, you mean like
Yeah.
a geometric point with zero size?
Infinitely small, yeah.
Yeah.
And infinitely dense. That's the singularity. It's this theoretical spot where, honestly, our current understanding of physics kind of breaks down. Density and gravity become infinite.
Wow. Infinitely dense, zero size. That's mind-bending.
It really is.
And that singularity, that point, is hidden inside the event horizon, right? The famous part.
Yep, that's the boundary. But it's crucial to remember it's not like a physical surface you could, touch or crash into.
Not a shell or anything.
No, it's a theoretical line in space-time. It marks the distance from the singularity where the gravitational pull becomes so intense that the speed you need to escape, the escape velocity, becomes faster than the speed of light.
Which is about, what, 299,792 kilometers per second? The universe's speed limit.
Exactly. And since nothing we know of can go faster than light, anything that crosses that boundary light, included, can't get back out. It's trapped.
The ultimate one-way street. Okay, and the size of this horizon, it depends on how massive the black hole is, that Schwarzschild radius thing.
Precisely. It
Yeah.
scales directly with mass. So for a small black hole, maybe one born from a single star, say 10 times the sun's mass, its event horizon might only be about 30 kilometers across, like the size of a city.
Tiny, cosmically speaking.
Yeah. But then you look at a supermassive black hole, like Sagittarius A, at the center of our Milky Way.
That's the big one, right? Millions of solar masses.
4.3 million times the mass of the sun. Its event horizon. It stretches out around 12 million kilometers. Much, much bigger.
That's a huge difference. Okay, so if light can't escape, how do we even know they're there? How do scientists actually find and study them?
We see their effects on stuff around them. Their gravity is so immense it pulls in nearby gas and dust.
Right, the accretion disk.
Exactly. And as that material spirals in, it gets incredibly hot due to friction, glowing fiercely, especially in X-rays, we can detect that glow.
Okay.
Plus, their gravity warps space-time itself so much that it can actually bend the path of light from stars or galaxies located behind the black hole from our point of view. It acts like a lens.
Gravitational lensing. We've seen pictures of that, haven't we? Distorted galaxies and stuff.
We have. It's direct evidence of that space-time warping. And that's essentially how projects like the Event Horizon Telescope managed to get that incredible image back in 2019.
That wasn't the black hole itself, though, was it?
No, you can't image something that traps light. What they captured was the shadow or the silhouette of the event horizon against the bright, glowing background of that superheated material swirling around it. A landmark achievement.
Absolutely incredible. Okay, so we know how they form, roughly, and their basic structure, singularity, event horizon. Now, the main event, pardon the pun, what did the sources say about actually approaching that point of no return? Is it that sudden vacuum cleaner effect?
No, not really.
Right.
It comes back to Einstein, his general theory of relativity from 1915. Gravity isn't just a simple pull. It's the curvature, the warping of space-time by mass.
Right.
So as you get closer to a massive object like a black hole, you don't just feel a uniform tug. What becomes critical, especially with black holes, is the difference in the gravitational force across your body or
Right.
your spaceship, whatever's falling in.
The difference, you mean like your feet being pulled harder than your head?
Precisely. That's the gravitational gradient, or what we call tidal forces.
Ah, tidal forces. Like how the moon causes tides on Earth, but amped up way beyond belief.
Exactly that principle. Gravity gets weaker with distance. So the part of you closer to the black hole's center feels a significantly stronger pull than the part farther away. And near a black hole, that difference becomes absolutely enormous.
Yeah.
Astronomical.
And this is where things get, well, messy. This leads to that famous, rather graphic term, spaghettification.
That's the one, yeah. Physicist John Wheeler apparently coined it back in 1967, and it's disturbingly accurate.
Okay, describe it. What does that mean?
It means that intense gravitational gradient stretches you vertically along the direction towards the black hole center, pulls you apart like spaghetti.
Stretched thin.
Very thin. And at the very same time, it compresses you horizontally, squashing you from the sides, because the parts of your body slightly off that direct line to the center are being pulled inwards towards that center line more strongly than they're being pulled purely down.
So stretched vertically, squeezed horizontally. Simultaneously, that sounds unbelievably violent.
It is. Utterly destructive. And here's the really crucial bit that our source material points out. Demolishing that quick vanish myth, especially for the smaller stellar mass black holes.
What's that?
Those tidal forces, the spaghettifying forces, they become overwhelmingly strong before you even reach the event horizon.
But hang on. You're saying you get torn apart before you even cross the point of no return?
For a typical stellar mass black hole, yes. The sources give some chilling numbers. For something like a 10 solar mass black hole, even when you're still, say, 1,000 kilometers away from the event horizon, the tidal force difference between your head and feet could already be over 1,000 times Earth's gravity.
1,000 G's difference just across a human body.
Easily. More than enough to just rip you apart. The chemical bonds holding your molecules together just give way. And if you get within, say, 100 kilometers, the sources suggest those tidal forces could reach millions of G's.
Millions. So there's no surviving that. You're basically disintegrated.
Atomized, essentially. It's a brutal physical disassembly, not a gentle fade to black.
So the opposite of the vacuum cleaner. Not sucked in, more like shredded on the way down.
That's a much more accurate, if grim, picture.
Yeah.
Cosmic shredder.
Okay. Wow. Now, you mentioned relativity earlier. There's more weirdness, isn't there? Something about time.
Ah, yes. Essential for black holes. Time dilation. Another consequence of Einstein's theory.
Right. Gravity affects time.
Massively so, near a black hole. So imagine someone watching you fall in from a safe distance far away.
Okay.
To them, as you get closer and closer to the event horizon where gravity is getting incredibly strong, your time would appear to slow down.
My time slows down from their perspective.
Yes. You'd seem to move slower and slower, taking longer and longer to reach the horizon. In fact, from their viewpoint, you'd appear to almost freeze right at the edge, never quite crossing it.
Like being stuck in slow motion forever.
Pretty much. And the light coming from you would get stretched out, redshifted, becoming fainter and fainter until you effectively disappear from their view, smeared out across the horizon.
So from the outside looking in, I just hang there, reddening and fading.
That's the external observer's perspective, yes.
Mm-hmm.
But here's the twist. From your perspective, falling in.
Yeah. What do I feel?
Time feels completely normal to you. Your watch ticks at its usual rate. You don't feel time slowing down at all.
So I just keep going.
You keep going, you feel the accelerating pull, you feel those rapidly increasing tidal forces
The spaghettification.
building up in real time from your point of view. And for that stellar mass black hole, that shredding happens very quickly and before you perceive yourself crossing the event horizon.
Wow. So my reality and the outside observer's reality are totally different at that point? That's bizarre.
Welcome to relativity near a black hole. It gets weird.
Okay, you keep mentioning stellar mass black holes for that shredding before the horizon scenario. Does it work the same way for the really big ones, the supermassive ones?
This is where size really does matter. It changes the experience right at the event horizon itself. Because a supermassive black hole is just so much larger, its event horizon is much, much farther away from the central singularity.
Right, millions of kilometers instead of tens.
Exactly. And because you're so much farther from the singularity at the point you cross the event horizon, the difference in gravity across your body, the tidal force, is actually much weaker there compared to the horizon of a small black hole.
Weaker, so maybe not instantly lethal.
Potentially, yes. For a supermassive black hole like Sagittarius A, the tidal forces right at the event horizon might be gentle enough for a human or even a spaceship to cross without being immediately torn apart.
So you could actually fall through the event horizon intact.
It's theoretically possible, yes. You could cross that point of no return in one piece.
That doesn't mean you're safe, right?
Oh, absolutely not.
Yeah.
You've still crossed the point of no return. You are now inside, and your fate is sealed.
Yeah.
You are inevitably falling toward the singularity.
And as you get closer to that central point,
Those tidal forces start ramping up again, incredibly steeply. Long before you actually reach the singularity, even inside a supermassive black hole, the spaghettification forces will become overwhelming and you will be torn apart.
so the end result is the same, complete disintegration.
The end result is the same. The only difference is where the lethal spaghettification happens relative to the event horizon. For stellar mass, it's before or right as you reach it. For supermassive, you might cross intact, but you get spaghettified later, deeper inside, on your way to the singularity.
Got it. Crossing the horizon might be momentarily less traumatic for a big one, but the final outcome, still shredded.
Still shredded. And what happens inside that horizon, especially down near the singularity, that's where our current physics really hits a wall. General relativity predicts it, but can't fully describe the conditions there.
Right. Infinite density, breakdown of known laws, the source mentions that. What else do we think might be going on inside or around these extreme objects beyond the horizon?
Well, there are some fascinating, though highly theoretical, ideas. Stephen Hawking's work in 1974 proposed Hawking radiation.
Yeah, the idea that black holes aren't perfectly black, they evaporate.
Exactly. Through quantum effects right near the edge of the event horizon, they might very, very slowly leak particles and energy, effectively evaporating over truly immense timescales, like trillions upon trillions of years or more.
So, interesting physics, but not exactly a rescue plan if you're falling in.
Not remotely relevant on human timescales? No.
Oh.
But it's profound because it links general relativity, quantum mechanics, and thermodynamics. Then there are other effects we do observe, confirming the space-time warping.
Like the lensing we talked about.
Right, gravitational lensing. We've seen stars orbiting Sagittarius A have their light affected exactly as predicted, like observations from the gravity instrument in 2018. There's also the photon sphere,
Photon sphere.
a region outside the event horizon where gravity is so strong that photons, particles of light, can actually be forced to orbit the black hole, temporarily trapped.
Light orbiting something. Wow.
And if the black hole is rotating, which we expect most are, they're called Kerr black holes, things get even weirder. There's a region outside the event horizon called the ergosphere.
Ergosphere.
Yeah, where the rotation of the black hole is so powerful it actually drags space-time itself around with it, like stirring a cup of coffee, but with the fabric of reality.
Space-time is being dragged around.
Yes. And theoretically, it might even be possible to extract energy from a rotating black hole via something called the Penrose process, exploiting that dragged space-time. Still theoretical,
Yeah.
but it shows how dynamic these objects are.
So they're definitely not just passive holes. They're these incredibly active, extreme environments, warping reality, driving bizarre phenomena. They're like natural physics labs.
That's a perfect way to put it. They push gravity and space-time to the absolute limit, forcing us to test and question our fundamental theories in ways we can't do anywhere else.
Okay, so let's circle back and kind of wrap up the main question. Based on everything in the sources, the realistic answer to can you survive falling into a black hole is a clear no.
For a human being, based on everything we currently understand, yes, it's a clear no. Spaghettification seems unavoidable. Whether it gets you before, at, or after the event horizon depends on the black hole's mass, but it will get you.
And those sci-fi ideas, like maybe finding a wormhole inside.
Highly speculative. The sources mention theoretical work, like by Kip Thorne, exploring wormholes as potential shortcuts through space-time, possibly connected to black holes. But there's absolutely no observational evidence they exist in a way we could actually use. The physics is way out there, maybe requiring exotic matter or conditions we don't know are possible. It's fascinating thought experiments, but firmly in the realm of theory, not survival guides.
Right, pure sci-fi for now. So if we can't survive them, why pour so much scientific effort into studying these, lethal objects? What's the bigger payoff?
Because understanding them is fundamental to understanding the universe itself. They are extreme test beds for our most important theories, general relativity, quantum mechanics. Trying to reconcile those theories, especially at the singularity, is one of the biggest goals in physics.
Finding a theory of everything, basically.
It's a key piece of that puzzle, yes. And people like Roger Penrose won the Nobel Prize in 2020, specifically for proving mathematically that black hole formation is an inevitable consequence of general relativity under certain conditions. They're not just theoretical quirks. They must exist if relativity is right.
So they confirm our theories, but also show us where the theories break down and need improvement.
Exactly. And they aren't just theoretical curiosities sitting out there alone, especially the supermassive ones. They sit at the heart of most large galaxies, including ours. And they profoundly influence how galaxies evolve.
How so?
Their gravity shapes the orbits of stars around them. But also, the energy and radiation blasting out from their accretion disks can affect star formation throughout the galaxy, sometimes triggering it, sometimes shutting it down. Recent observations, like with Hubble in 2023, keep showing these complex feedback loops between supermassive black holes and their host galaxies. They're active players in cosmic structure.
So studying them tells us about galaxy formation and the universe's large-scale structure, too. It's not just about the object itself.
Precisely. The complexity we see, spaghettification, time dilation, frame dragging, their galactic influence, it paints a much richer, more intricate picture than just cosmic vacuum cleaner. It forces us to move beyond those simple popular myths.
Yeah, the reality is far weirder and honestly more interesting than the fiction.
Definitely more interesting.
Okay, so wrapping up this deep dive, the main takeaway from the sources seems pretty clear. Black holes are anything but simple. They're these zones where gravity completely warps reality in ways that are, frankly, extreme and violent for anything getting too close.
Right. That approach isn't a quick vanishing act. It's a complex, brutal process dominated by tidal forces and ultimately spaghettification.
And while survival, for us, is off the table,
Complete.
the scientific quest to figure them out, that's absolutely crucial. It seems like they hold some major keys to understanding the fundamental workings of the cosmos.
They really do. Unlocking their secrets is unlocking secrets about gravity, space-time, and the universe's history and future.
And maybe it leaves you pondering this thought, given that singularity, that point where all our known physics just seems to collapse, what totally new kinds of physics, what new understanding of reality itself might actually govern what happens inside that infinitesimal point, even if we can never ever go there to see it directly?